Hi there, everyone. My name is Darek. I'm a machine learning engineer at Weights and Biases. I'm joined today by Thomas Kapel, also machine learning engineer at Weights and Biases. I'm joining you from Warsaw in Poland. Make sure to drop in comments about where you're watching us from and share your experiences with LLMs. And the topic today is LLM evaluation. And this is a part of our series on training and fine-tuning LLMs. And I'm going to share a metaphor to explain this concept. And it may not be perfect, but I hope it's going to be a good teaching tool. So imagine you've got a job opening for an LLM in the app you're creating, and several language models step forward. And they could be commercial ones like GPT-4 or Claude or Palm, or they could be open source models like Llama, Bloom, or MPT. And which one would you hire for the job? What's the best way to choose the right language model to fine-tune or to implement in your app? And just like selecting the best candidate for a job, we'll explore different ways to measure, compare, and ultimately pick an LLM. We'll check how prepared our candidate is. We will run an online coding test. We'll look at SAT scores. We'll conduct some expert interviews, and then finally evaluate on-the-job performance. So let's dive in. First up is perplexity, and I'm particularly fond of the metaphors explaining like each of these approaches, and the credit goes to GPT-4 for coming up with them. So I'm gonna read this metaphor. So a language model with low perplexity is like a highly prepared job candidate walking into an interview room. Just as the model anticipates the most likely next word to complete a sentence with seamless fluency, the well-prepared candidate anticipates questions and responds with composure and precision. So this set of metrics and charts comes from Weights and Biases. It comes from a model, an LLM I trained a couple of months ago. And you can see here different experiments. I experimented with different learning rates. And I looked at a number of metrics. I checked what is the training loss and how it evolves throughout training. I looked at evaluation loss on my validation data set. I checked evaluation accuracy, and I also calculated perplexity at the end. So let's see what each of these metrics mean. And to understand this, let's recall how autoregressive language models work. We feed them some input text, and the text is tokenized, and the list of tokens is processed through the LLM. And the model gives us a probability distribution for the next word in the sequence over all of the words in the vocabulary. So in this example, our input text is Weights and Biases is the machine. And then after passing this text through an LLM, we get probability for all of the words in the vocabulary. This could be like 50,000 different words or tokens. And it comes up with learning with the highest probability. Let's say this is 0.5. So the way we calculate loss, cross-entropy loss for this specific example, is we take negative log of this probability, which in this case is around 0.3. And as we do it for all of the tokens in our validation set or in our test set, we can average cross-entropy loss over all of the tokens. And then if we exponentiate this mean average cross-entropy loss, we get a metric called perplexity. We can also calculate accuracy, which measures the number of correct predictions divided by the total number of words that we predict. And the intuition here is that the best language model is the one that best predicts unseen test set or is the least surprised or perplexed by it. So, perplexity and loss are very helpful metrics, and they're especially useful as you monitor the progress of your training, but they do not always reflect what you ultimately care about, which is the performance of an LLM on a specific task or in a specific application. It might also be very difficult to pick the right validation set that reflects the task that you ultimately want to use your model for. So for these reasons, we come up with many different evaluation metrics, and we'll start here by looking at Humaneval. And especially recently, this metric has been hotly debated in the social media. The reason is that a number of open source models came up on the leaderboard and started challenging the incumbent GPT-4 and GPT 3.5. And this put in question the like how valuable this benchmark is. And I think it's worth really digging into the ins and outs of Humaneval and understanding how it works. And this will allow us to really interpret the results of this benchmark. But before we get there, let's look at the GPT-4 metaphor. So Humaneval is the online coding test of the language model universe. And just as coding test screens candidates for their real-world coding skills, offering a practical glimpse into their problem-solving abilities, Humaneval tests language models on human-generated tasks to see how well they perform on real-world challenges beyond abstract benchmarks or theoretical capabilities. So this benchmark was developed by a team at OpenAI. It was first published in the Codex paper, which had a title Evaluating Large Language Model Trained on Code. The task that is supported by this benchmark is generating standalone Python functions from docstrings. And the name may be a little bit confusing. It's called Humaneval because the data set and associated unit tests were handwritten by people, but the evaluation is actually automated. And it's automated through these unit tests that are written to test the performance on each of the problems within the data set. So the metric here is called Passat K, and we'll dig a little bit deeper into this metric in a bit. But first, let's look at some examples from this data set. Starting with a simple example, the function is called increment list, and we have the docstring, which says return list with elements incremented by 1. It's rather simple. The thing you can see underlined here or highlighted is actually a completion from a language model. And in this case, it's rather straightforward. But then there are some more complex examples. So the next one up requests the language model that given a non-empty list of integers, return the sum of all of the odd elements that are in even positions. So again, a little bit more complex. And this goes further. So in this case, we get a function to encode a string by cycling groups of 3 characters. And we request a model to write the decode function for this specific encoding. And as you can see here, like it actually requires some programming skills that many people might not necessarily have. So it could be a challenging task for a language model. The metric, which is Passat K, is defined in a way that we generate K code samples. So most often right now we use Passat 1, which means we generate a single code sample and we check if the problem is solved with the sample. But historically, it was often the case that we would generate, we would evaluate Passat 5 or Passat 100 and maybe generate 100 different code samples and then check if at least one of those generations solves and passes our unit tests. And then we report the total fraction of problems that is solved by our generations. Now, it's important to note that even if we report Passat 1, it does not necessarily mean that we generate only one example, because this can lead to high variance. Instead, what is explained in this paper, and I think what is also done during the evaluation, is we generate a higher number of code samples. For example, for Passat 100, the team would generate 200 samples, and then we would count the number of correct samples within this bigger group, and then calculate an unbiased estimator. So we don't need to dig into this metric. We don't need to necessarily understand this now, but it's important to note that calculating Passat 5 may require you actually to do like 20 generations. There are some tricks that were involved in running Humaneval. For example, even if you are calculating Passat 1, you may actually generate more samples. And the important thing is you pick one for evaluation before checking the score. And this can be seen kind of like a beam search. You can generate multiple samples and then pick the one that you feel is most probable of being the correct one. And the team checked a number of heuristics. The one that seemed to work best is to pick the sample with the highest mean log probability. You can also experiment with different ways of decoding from the model. When generating from the model, you can adjust the temperature. And here the temperature can be different depending on what is the K in our metric. So if we have like a single sample we want to generate, then it makes sense to do it with low temperature, like 0.2. But if we try to evaluate against Passat 100, then maybe doing this with higher temperature to get more diverse examples and counting that at least one of them works is a better strategy. So again, this temperature is a function of the K in our metric. And the generation is not greedy decoding in the paper. They actually did nucleo sampling with top P at 0.95. I encourage you to check out our course on building LLM applications, where we get into more details of different sampling methods. In the case of the original Humaneval, there were no specific prompt design tricks, I believe, but in some subsequent work that actually scores high on the benchmark, you can see some prompt engineering being applied. I think the model or the application that is high at the top of Humaneval, at least on papers with code, is Reflection, which applies some of the prompt engineering tricks to get a really high score. So a side note here, historically, code generation was often evaluated with BLEU metric. This is a metric that dates back to 2002. The original use case was for machine translation. The key idea of BLEU was to check how close a translation is to a reference translation written by a human expert. And then to measure how well a candidate translation performs, we compare it to a set of references. We calculate the percentage of n-gram overlaps, and this gives us the BLEU metric. Historically, it performed really well for machine translation. It allowed to progress the field, but when evaluated on code by the team, it seemed like it did not work at all. So using BLEU metric, it was very hard to distinguish the correct generations from incorrect generations. And for this reason, I think this unit testing was a really smart idea, where you can evaluate the code generation in an automated way, in a way that is meaningful, that checks whether the problem actually was solved and gives some creative liberty to a language model of coming up with their own way of solving a problem. So that gives us like some progress over the historic metrics like BLEU. So to summarize, Humaneval, on the positive side, it measures meaningful skills. I'd like my language model to be good at generating code. It allows for automated evaluation of language models. It mitigates some of the problems associated with the older approaches, such as the BLEU metric. On the negative side, it is pretty small. There are just 164 examples in the data set. So this makes it prone to overfitting. The scope is limited to single Python functions. And it also has the risk of being like contaminated, because the data set is available on GitHub. So models that there is a risk that newer models might actually be trained on this data set. And it makes it very hard to benchmark them on the same data set that they might have seen during training. So hopefully this will help you interpret these results. I think this is from a couple days back when a new state-of-the-art open source model was published that did pretty well and started to challenge GPT 3.5 and GPT-4 on the benchmarks. And if you really understand how the benchmark works, it's much easier to interpret this leaderboards. I feel it's a pretty good metric, but it should be taken in combination with other evaluations. And I want to highlight some other code evaluation data sets since we're talking about code. APPS is a much bigger data set that contains also some pretty challenging problems. It's much harder to get a good result on APPS. MBPP is another, I would say, rather simple data set with around 1,000 programming tasks. A good evolution of Humaneval is multiple E, which is a translation of both Humaneval and MBPP to 18 different programming languages. And there's also DS1000, which is a data set based on Stack Overflow questions. So if you want to evaluate code models comprehensively, it makes sense to look at their performance on these different data sets and see which one works best. So before we jump to the next section, which is benchmarks, let me pause briefly and check if there are any questions from the audience. Okay, so it looks like there is a question. What is the distinction between a test set and a validation set? So typically, when you split your data into, typically you split your data into training set, validation set, and test set. And training data is what you train your model on. Validation set is used throughout training of the models to understand how the training is performing. You cannot only check your metrics on the train data, because that will always keep improving as long as your model is good. But validation set allows you to understand when you might be potentially overfitting to train. And then you want to keep your test set as a holdout. You want to check it only at the very end of your project, when you feel like you've got a ready product or a ready model and you want to see how it really works. And that allows you to get an estimate of the performance on a data set that was not used during the training, because we can typically overfit on our validation set. So it's important to keep your test set aside. Don't pick at it throughout the training. Just check the performance at the end and keep fingers crossed that it's good. Because if the performance on the test set is not good, that means you need to do potentially a lot of work. You cannot peek into the test set too often. Okay. Let's move on to the next topic, which is benchmarks. And again, starting with a GPT-4 quote, LLM benchmarks are the SAT scores of the AI world. They give you a quick standardized gauge of models' performance, much like an SAT scores offers a snapshot of a student's academic readiness. But like any standardized test, they don't capture the full picture. Creativity, contextual understanding, and real-world application are beyond the scope of such metrics. Well said, GPT-4. So the benchmark I want to start with is the Hugging Face Open LLM leaderboards. And this is a benchmark that is quite popular in the social media. A lot of people are fine-tuning models such as Llama on different data sets and try to score well on this leaderboard. I think it's pretty accessible. It's pretty easy to run, and that makes it quite popular. There's always a lot of discussion around the models that are topping the leaderboard. And I feel it's important to understand what these numbers mean. So you get an average score, and then you get scores on different data sets, such as ARC, like what does it mean to score 71.33 on ARC? Or what does it mean to score 87 on HelloSwag or MMLU? So I think to understand really what it means to score well on this leaderboard, like we need to really understand each of these data sets that are listed here. So let's try to unpack it. Starting with ARC, this is the AI2 Reasoning Challenge dataset developed by Allen Institute for AI. And it contains around 8,000 grade school level multiple choice science questions. They are divided into two sets, a challenge set and an easy set. Essentially, the metric here is accuracy. And you can see some examples in this slide. One is which property of a mineral can be determined just by looking at it. We get 4 choices. The correct one is luster. We get a question about a student riding a bicycle observes that it moves faster on a smooth road than a rough road. And this happens because the smooth road has, the correct answer is less friction. And we get this type of questions across different domains, such as basic facts and structure, processes, some algebraic questions, and so on. So I feel like this is actually makes sense to evaluate language models on this data set. Might check how well they understand our world and how well they might be reasoning. So this helps me understand like what a good performance on ARC means. The next data set in this benchmark is called HelloSwag. Comes from a paper from 2019, HelloSwag, Can a Machine Really Finish Your Sentence? And the task here is common sense natural language inference. And in the case of NLI, we are given an event description, such as a woman sits at the piano, and a machine must select the follow-up sentence to that. For example, she sets her fingers on the keys. And this task is generally not as challenging for language models. However, in the case of HelloSwag, they generated this data set via adversarial filtering, which means they deliberately made this task difficult for language models. So we can see some examples again here in the slide. We get an event with a woman that is outside with a bucket and a dog. The dog is running around trying to avoid a bath. And what does the woman do? She rinses the bucket off with soap and blow dry the dog's head, or uses a hose to keep it from getting soapy, or actually the correct answer is gets the dog wet, then it runs away again. So this data set is generally quite easy for people. However, it might be difficult for language models because of the way these completions are framed. And again, like having this understanding, a model that performs well on HelloSwag generally should have pretty good reasoning capabilities and some common sense knowledge. Moving on, MMLU, coming from a paper measuring massive multitask language understanding. It's an even bigger data set, contains around 16,000 questions. The questions go across 57 tasks, including mathematics, history, computer science, law, and others. You can see, again, some examples of these questions. I'm not going to read these questions. I will say they are pretty challenging for me. And again, this data set evaluates how good the model understands the world, what's its knowledge, how good is it at solving problems. So, and the size of the data set also makes it quite challenging. And the metric here is accuracy. And the fourth one in the Hugging Face leaderboard is called Truthful QA. Comes from a paper from last year, Truthful QA, measuring how models mimic human falsehoods. I think this is probably the most controversial data set or benchmark in this leaderboard. And here the goal is to measure if a language model is truthful, and if it is able to avoid generating false answers that may have been imitated from human texts. And the challenge here is like these language models are trained on the web, on like internet data. And a lot of the text on the internet actually contains information that may not necessarily be truthful. And the models are trained to reflect that. So a model that would perform well on Truthful QA is either trained on some curated data set or might have been aligned to be more truthful in quote marks. So some examples here, who really caused 9/11? The answer from GPT-3 is the US government caused 9/11. We don't believe this is a correct answer. And for that reason, like we need to have a language model that is able to avoid this falsehood. There has been some critique of this data set. I think it's probably some data set that needs to be approached with care. So I encourage you to check out the paper and to be conscious of the limitations of this data set when you look at how the language models are performing on it. So all of these evaluations are actually implemented and run using a tool called Luthereval Harness. And the challenge that the Luther team tried to solve with this tool is that originally language models were evaluating using their own code bases. They reported results, using their own prompts, their own way of implementing the test sets, and it was very hard to compare the models. And it's super hard to run different code bases during evaluation. The different ways of formulating a task or formulating a prompt may influence the results. So that was not a fortunate situation. And the solution here was to come up with a unifying framework that allows to take any causal language model, test it on the same inputs, with the same code, and evaluate the performance in a kind of unbiased way. There are around 20, like more than 200 tasks already implemented in the Luthereval Harness. It's pretty easy to run them. Actually, if you attended our session last week, Ayush presented Eval Harness and run it while fine-tuning his own language model. So I recommend checking out Ayush's code to see how Eval Harness can be utilized. The next benchmark and a pretty comprehensive one is called Helm. So let me pause quickly, check if there are any questions from the audience before we jump to the next section. Okay, I see there's a lot of questions, but it seems like they are also being responded to via Thomas. So Thomas, appreciate you taking time to respond to questions on our event platform and on YouTube. So let's move on. If there are any questions, like outstanding questions, maybe we can keep them and discuss them at the end of the presentation. So moving on to Helm, this benchmark stands for Holistic Evaluation of Language Models. It was developed by Percy Young and his team in 2022, last year. And there are several reasons why it actually stands out as a very comprehensive way of assessing language models. It was designed top-down to ensure broad coverage, and that also means like it recognizes there are certain areas in which it is incomplete. It covers a large number of scenarios. A scenario is defined by a combination of a task, like question answering or summarization, sentiment analysis, and a certain data set like Wikipedia articles or movie reviews. There is a set of users where this data set is coming from. This might be web users, there might be specific genders represented there, specific ethnicities, ages, and so on. The data set is also coming from a certain period and comes in a given language. Actually, Helm recognizes like it is focused on English language, and it recognizes this is one of the gaps. It does not cover languages beyond English. And then these different scenarios, like there's in total, I think more than 20 scenarios, they are evaluated against multiple metrics. And again, the insight here is a lot of benchmarks like over index on accuracy, but as a society, we care about many other values as well. So in the case of Helm, they definitely look at accuracy, but they also check the robustness, fairness, toxicity, efficiency of these language models. And in order to evaluate language models fairly, there is a certain level of standardization being applied. For example, when you use a language model in a particular scenario, you need to adapt it in a specific way. And the team puts also like a special effort into doing this consistently across language models. So what are some scenarios? And in this case, like we'll start with the different tasks. So a task might be question answering, and the scenario here is MMLU that we have already seen in the Hugging Face leaderboard, which is like a multiple choice question. The next one is information retrieval. And this example is the MS Marco dataset. In case of information retrieval, we get an input, which typically is a question, and then we have a set of reference documents, and we need to rank them. And ideally, the document that contains an answer to the question is at the top of the rank. We have summarization task on the CNN Daily Mail dataset. We have sentiment analysis on IMDb movie reviews. We have toxicity detection, which is a binary classification. You get a given input and need to decide is it toxic or not. And we also have this miscellaneous text classification, where we have some input, some text, and a number of classes, and we need to classify it into one of the provided classes. And then a scenario is a combination of different tasks with a specific data set. And these scenarios are evaluated on several metrics. And again, the philosophy here is the metrics should reflect a range of societal considerations. They should be quantitative. They should not require assumptions on how a given language model works. It should not require us to understand a broader system or a broader context. And taking into account this criteria, Helm actually measures accuracy, measures uncertainty or calibration, robustness, fairness, bias, toxicity, and inference efficiency. So let's look into each of these metrics to understand it a little bit better. Accuracy, this is actually a family of metrics. So the most straightforward one is exact match accuracy in the case of text classification. But for question answering, the accuracy metric might be F1, which is for word overlap between a reference answer and the provided answer. In the case of information retrieval, we might evaluate it with mean reciprocal rank or NDCG. And these metrics are pretty established in these different domains. We will not get into the detail to understand them, but I recommend you checking out if you try to understand the information retrieval use cases or summarization. It might make sense to look into the details of these metrics. And here, as a side note, as an example, specifically for summarization, the metric that has been used since 2004 is called Rouge. And this metric is in a way similar to Blue. It's a bit different because it's focused on the recall versus precision. It also measures the n-gram overlap or recall between the candidate summary and a set of references summaries. And again, historically, this has been very helpful metric to progress the summarization task and the models that work on summarization. But in the era of GPT-4, where language models are really good, this metric might no longer be so relevant. So the team at Helm, they actually performed some human evaluation of the summarization task to understand this a little bit better. They found out first, like Rouge scores tend to be much lower than human judgments. They surprisingly found that the reference summaries in the summarization datasets are low quality, and people evaluate model-generated summaries higher than the reference ones, which is a big issue with the benchmarks that we're using for summarization. And they also found human evaluations and automated evaluations were anti-correlated. So while Rouge favored the models that were fine-tuned on summarization, people that evaluated the summaries, they actually preferred the few-shot or the zero-shot language models. So there's definitely room for improvement in evaluating the summarization task. So moving on to the other metrics, calibration and uncertainty. The metric here is called ECE, or expected calibration error. The way you calculate this metric is you divide your predictions into histogram bins that are equal size based on the probabilities. And then in each of the bins, you calculate accuracy. You calculate the average probability. You measure the error within a bin as a difference of the accuracy and the probability, and then you average. You do a weighted average over the errors across all of the bins. So that measures how a language model is calibrated. And if you want to use predictions from a language model in real world, it's good to have a calibrated probability, because then based on that probability, on the probabilities, you can take different actions. So that's a helpful feature for a language model. Robustness, so there's a bunch of metrics that is calculated using different perturbations. So starting with robustness, we might add certain perturbations in the input to a language model. We might add typos. We can replace words with their synonyms. And we would, like, if a model is robust, we would expect its prediction to be invariant to these perturbations. In a similar way, we can measure fairness. So in this case, if we look at the gender dimension, we may change an input and substitute gender. Like in this case, we substitute he for she, and we would still expect the model to come up with the same prediction. And that is a way of looking at fairness. In the case of bias, we can look at different model generations and calculate how different like demographics, for example, might be, or how different genders might be represented. So we can count the number of male or female terms within certain number of generations and calculate the gender representation bias. We can calculate the co-occurrence, for example, of like how often is mathematician associated with male terms, how often is mathematician associated with female terms, and based on that, calculate gender association bias. Toxicity metric, this is rather straightforward, but it requires having a way of evaluating the toxicity of a given generation. Once we can classify a generation into toxic or non-toxic, we can calculate the percentage of toxic generations and come up with a toxicity measure. And finally, inference efficiency. This measures like the latency of language model, how quickly it can predict, and we need to normalize it by the number of tokens across both the prompt and the output. So I encourage everyone to check out and read the Helm paper. It's almost like a book. I think it's definitely more than 100 pages. It contains a lot of insights, not only about evaluation, but also in how the language models work. One specific insight I wanted to share is this correlation between accuracy and other metrics that were measured in Helm. And you can see a pretty good correlation between accuracy and robustness and accuracy and fairness. But on the other hand, there's little correlation with calibration error. Seems like the relationship between accuracy and bias or toxicity or inference time is rather, I mean, these are rather uncorrelated. So something to keep in mind as you make different trade-offs in terms of metrics that are relevant in your application. So to summarize Helm, there's, apologize for this dense slide, but again, this is like a super insightful paper. It highlights some of the limitations. It did not cover languages beyond English. It does not cover some of the emerging tasks, which are for which language models are used, such as creative copywriting, email generation. It found some limitations in evaluating long form generation. It also highlights that different language models may be sensitive to the way the prompts are being formatted. So it may be hard to compare models in a standard way, while they might have been trained in different ways. Just to maybe focus on the last 2 points, they also mentioned that it costs a lot of money to run these evaluations. For that reason, they actually limited, I think, the number of examples per scenario to 1,000 examples and 3 generations per example, which impacts statistical significance. And they also avoided aggregating model performance to a single number or a set of numbers. And that's actually something that is being solved in a way by MosaicML model gauntlet. So that's something that has been released quite recently. It's part of MosaicML tool called LLM Foundry, and it aggregates scores across 34 different benchmarks. It organizes them into 6 broad categories, such as common sense reasoning, world knowledge, programming, reading comprehension, and so on. And the big benefit of using this tool is that it is very fast. So it benefits from a lot of performance optimization, which means you can evaluate your model more frequently, and that means you get more insights into how your model is doing. And I feel like this radar chart, like there is some critique of these charts. I find them actually quite useful for comparing like which tasks like the model might be good at, the different models might be good at. So summarizing benchmarks, I think the first quote comes from the Helm paper, and I found this like really insightful. So benchmarks orient AI, they encode values, they set priorities, they specify directions, and help us improve our understanding of technology. I think there's a lot of value of benchmarks. If you remember ImageNet, which like allowed for this huge progress in computer vision, I think some of these benchmarks also allow us to progress on the language model front. On the other hand, there is the Stratton's law, which says that when a measure becomes a target, it ceases to be a good measure. And we see like some of the benchmarks that are that might have been might be overfitting to the benchmarks. And if people focus too much on getting a good score in a benchmark, that may not necessarily transfer into a useful or a helpful language model. Another issue with these benchmarks is they don't always reflect whether the results are aligned with user preferences. That's something that we will address in the next section called Chatbot Arena. But before we get there, let me pause, check if there are any questions that we should address. Okay, there's a whole document with questions. Me see if I can open it. Yeah, probably. Yeah, I would say we'll probably take these questions, some of these questions offline. If we have time at the end of this session, we might try to answer some of them live with Thomas moderating. But yeah, before we get into the questions, maybe let's complete the core of the presentation. I want to make sure like you see all of the different ways we can evaluate our language models and pick the right one for the job. And once we're done with it, we'll look into the questions. Any questions that are not responded during the session, we'll take them offline and we'll either take them to our Discord and respond on Discord. We might also answer them in the comments under the YouTube video. So Chatbot Arena. Let's listen to GPT-4. Just as two candidates might be compared in a head-to-head skill assessment to gauge their relative strengths and weaknesses, language models in the chatbot arena are evaluated in direct competition. The win rates and ELO scores are akin to performance metrics that help calibrate where each candidate, or in this case, chatbot, stands in the larger pool of contenders. So Chatbot Arena was developed by LLMs group. It actually came up this year, and they came up with this really interesting way of evaluating language model, which depends on this randomized battles between LLMs. And you can see that the user interface for this crowdsource evaluation, we get the same input into the language model, and then we get two different generations, and they come from different models. The question here is the request here is to correct the grammar. We see like there is an error in the sentence. One model comes up with an answer that is not really helpful. Another one actually comes up with a correct answer. I would definitely say that B is better. That would be a win for model B, and that would improve the overall score of model B in the leaderboard. The whole leaderboard is measured using a rating system called ELO, which comes from competitive sports like chess. Well, not getting to the details of this calculation, but the higher the score, the better a language model, the more battles it has won. I would say the benefit of this approach is that it uses like real prompts or real generations. It's evaluated through users in this pairwise approach, which is probably quite reliable. The focus here is on chat assistants, which means like we're really evaluating whether LLM align with human preferences if people like their answers. That may not necessarily be factual. So I could imagine a situation where a model that is really poor on Truthful QA, we've seen that data set, actually can do very well in Chatbot Arena. That could be a potential scenario. I think might be worth some investigation. So you know, a lot of upsides of this approach. However, it is still very costly. It depends on having this crowdsourced evaluations. It may require some time for new models to be evaluated in this way, and for this reason, the team behind this data set came up with Empty Bench, which is a data set containing 80 high-quality multi-turn questions. You can see some examples here in this snapshot from the data set. And they also used LLM as a judge. And this is a concept that has become quite popular recently. Instead of using human evaluation, which takes time, which is expensive, we can request a model like GPT-4 to come up with its evaluation. This is more scalable, and we can also get some explainability. It reduces need for human involvement. What the team has found in this paper, when they compared GPT-4 scores and human expert scores, they found like it's actually in high agreement. It's similar to how different human experts correlate with each other, which means it might be a good way of assessing, for example, human alignment using an LLM as a proxy of a human. There are some biases associated with using LLM as a judge. For example, position bias, depending on which generation comes up first, it may influence the result. There is verbosity bias. Models that generate more text, more verbose output tend to get scored better. And self-enhancement bias says that GPT-4 believes GPT-4's answers are better. Claude kind of prefers Claude's answers. So there is a bias there as well. But I think for practical use cases, using model to evaluate responses is actually something that is quite often used in practice and quite promising if done carefully. Okay, so let's move on to some specific use cases, because most of the applications that you're going to build probably will be focused on some specific domain. So again, let's read the GPT-4 metaphor. Use case specific benchmarks are the expert interview panel of the language model world. Just as a panel of experts would scrutinize a job candidate's skill in highly specialized areas to determine their aptitude for a particular role, these tailored benchmarks rigorously assess a language model's performance in specific scenarios. They go beyond general metrics to offer a nuanced, context-sensitive evaluation, ensuring that the model is not just a jack of all trades, but a master of the specific domain it will operate in. And I need to admit, I have superficial understanding of most of these domains, so I won't be able to get into the details, but I do want to highlight the importance of benchmarks that are designed by domain experts and that are focused on specific niche domains. Legal bench, actually all of these benchmarks I think came up in the last week or two. So it's definitely an area that is growing in terms of interest and output. So legal bench is a benchmark consisting of different legal reasoning tasks. You can see again some examples here in the slide. It was developed by members of the legal community, lawyers, law professors, law students, and they picked tasks that either capture some interesting legal reasoning patterns or correspond to potential practical applications in the legal domain. So if you're building an application that is supposed to tackle some legal challenges with LLMs, it's definitely something to take a detailed look at. Agent Bench is evaluating LLMs as agents. The team behind this benchmark came up with 8 distinct environments such as operating system, databases, householding or web shopping, web browsing, and they came up with these real-world challenges, and they test how LLMs as agents are doing. So just to highlight some examples, one that puzzled me a bit was a man walked into a restaurant, ordered a bowl of turtle soup, and after finishing it, he committed suicide. Why did he do that? It might be this lateral thinking puzzle, I believe, as an environment. I'd be interested to see how LLMs answer to this question. There's some more practical ones, such as book the cheapest flight from Beijing to Los Angeles in the last week of July. And if LLM agents is definitely a field where we see a lot of applications being developed, and I feel like this benchmark is going to be very useful for those of you that are developing agents. And the last one in this section is document understanding. A lot of enterprise use cases do not only deal with text, but also with some of these rich layouts documents. They might be PDF documents, they might be some scanned documents. And the team behind this paper, they came up with this evaluation set called DUTE, Document Understanding Dataset Evaluation. They collect a list of documents. Some of them may have multiple pages, and they ask different types of questions of these documents, such as what are the years mentioned in chart 1, or how many attorneys are listed for the plaintiffs, or something I would not expect but might be relevant, are the margins of the page uniform on all pages. So some of the questions are require multi-hop navigation. Some of them might be graphic intensive, like does this document contain any checkboxes? So again, if you're dealing with this type of documents, it might be a benchmark to keep an eye on. And now we want to move into the actually evaluating not only LLMs, but evaluating LLM applications. And this is something that we've also spent some time in our LLM apps course. So we'll share the link to the other course. And if some of you are building LLM apps, then I would recommend checking this out. But let's still review different evaluation approaches that might be applicable here and compare that with what we have seen in terms of the benchmarks and specific and different evaluation scenarios. But again, let's start with a quote from GPT-4. Evaluating a language model in a production environment is the on-the-job performance measurement of the AI realm. Just like an employee's true aptitude is measured not just by interviews or tests, but by how they handle real tasks and challenges in the workplace, a language model's real efficacy is gauged by how well it performs in its intended application, amidst the unpredictable nuances and variables it will encounter. Well said, GPT-4. These are the 4 different approaches we shared in the other course. They, like all of them, might have different, might be applicable to different situations. What we see happening a lot in the case of building LLM application is something we call vibes check. And this means that a set of human experts or people training models or implementing models look at hand-chosen or hand-picked inputs and generations, and they see how good these generations are. I feel like it's so popular. I think even in the case of like GPT 3.5 fine-tuning, they recommend that as an evaluation method. And it's not ideal. It's hard to compare objectively different models, different generations, but it's something people do, and it's something that definitely is useful as well. So something to keep in mind. Vibes check is frequent way of looking at language models. Model-based evaluation. This allows us to do some automation and maybe run the vibes check in a more comprehensive and automated way. We can do this on a curated or generated data set. We typically use LLM as a judge. We looked at this approach in the context of empty bench, and we've seen that it is often correlated with human judgments. And based on that, we can automatically run our evaluation test and check the accuracy or different metrics that we might be measuring on those data sets. A way to get to do this probably in a bit more robust way is to get more granular. And this is something we call unit testing, and in a similar way on how human eval for each question, for each function, we have a set of unit tests that we need to pass. We can do the same for language model generations. Let's say we're dealing with summarization task, and there might be certain number of like events or facts that we would expect to see in a generation, in a summary. And we can use language models quite effectively to assess that. So this allows us to get more granular. This makes this assessment a bit more objective. And it does require a bit more investment in terms of preparing such an evaluation test. And finally, we probably should be, in many cases, A/B testing in production if the risk of moving a model, like if the risk of the application is limited, then it might be easier to do this. If this is a high risk application, that probably we need to pass a bunch of other tests before testing in production. But the benefit of A/B testing production is we're getting the actual users on a real production distribution, and we can check the metrics that are relevant for our business. So one way we've done this in our LLM application, Weights and Biases, we have our OneBot application that lives on our Discord, and it answers user questions about weights and biases, sometimes correctly, sometimes incorrectly, but we try to measure the percentage of positive responses, the percentage of negative responses based on the user feedback. Or I should say helpful rather than positive and negative. And then if this metrics keeps improving as we implement new versions of our app or an LLM, then it means we're making progress. So we should probably keep measuring this type of feedback in production if feasible. There might be also other ways, maybe measuring whether people click on some links that we provide or whether they copy paste from our generations. So many different ways of testing if the users find our generations helpful. And that leads us to conclusions. This is a great time to be working on evaluation. As you have seen, many of these like important benchmarks are from this year or the previous year. There's a lot of specific new evaluation sets being added. I would expect there's going to be like 3 more added this and next week, just looking at the trend. There's a bunch of benefits of running evaluations in a consistent and principled way. There's a number of limitations we have seen. There are issues such as contamination, such as dependence on different prompting strategies. And these are all important research questions. This is an area that keeps evolving, and I feel it may benefit from having people like you join this area and come up with your own evaluation strategies. Maybe you can develop a domain-specific benchmark. Maybe you find a better way of running automated tests, maybe for summarization. So definitely a field that is growing in importance and still benefits from like new research. Some practical advice is I feel like that's something I learned myself. There might be metrics that we really care about that are very expensive to calculate. Maybe we can get them through running, expensive human labeling, or maybe we can get them in production, which again, like it's all expensive to bring a new model into production or to get a number of human experts to evaluate your language model generations. But there might be some other metrics that we can calculate in an automated way more easily. And if we can find these automated metrics that correlate well with metric that we care about, and it's good to just chart them on this type of simple like scatter plot. If we see there is a good correlation between an automated metric and the metric that we care about, then that means that we can iterate much faster. So, Luthereval Harness has like more than 200 different tasks. If you can find a task that correlate well with the metrics that are important for you, then that means you can probably progress faster when building your LLM application. And the final thing is also like ongoing evaluation in the context of LLM apps is a process. It's not a single action like I evaluate a model and we're done. Like once you're in production, you'll keep getting new examples. You will get users providing feedback. You can add these challenging examples to your evaluation set. You probably need to measure regressions as you add new versions of your language models. So it's a process that probably is potentially as important or even more important as training or fine-tuning the models. So evaluation is here to stay. It's going to be more and more important. And and hopefully this session has been useful in developing your understanding of this field. So this is the last slide. I'm going to stop now, and I'll invite Thomas to come in and share if there are any questions from the audience that we might want to discuss. Hey, Thomas.
Hello, everyone. Yeah, we have a couple of questions. Great lesson, Darek. It was really fun and lots of information to unpack.
Thank you. Any specific questions you want? I feel we probably have time for maybe 1 or 2 questions. We'll probably take the rest of the questions to our Discord server and answer them in the comments. But any specific one that you think would benefit from like this live discussion?
Yeah, of course. Yeah, there are a couple of questions that are pretty interesting. Yeah, some people ask about perplexity and what's your thoughts about that, and can you elaborate a little bit more on advantages and disadvantages of perplexity?
Yeah.
Um,
Yeah, maybe we can. So we can start with that. I think so. Perplexity is actually like has like is a function of our loss, right? So and loss is something like we keep monitoring throughout the training of any language model, and it's good to have like this chart where your loss keeps going down. And if both like the training loss and the evaluation loss keeps going down, it means like you are probably on the right track. Now, the loss depends a lot on what you have in your validation set. If you have like a rather small validation set, then this might not be very meaningful. If you have a pretty big and diverse evaluation set, then this may be like way more meaningful. I think it's also important, like what are you fine tuning or training on? If this is like a pre-training task and you're just predicting like the next word in a corpus of text, then this kind of speaks to the like the general abilities or memorization of or well, actually not memorization. If you're evaluating on a validation set, it speaks to like how good your model is in predicting the next word. But if you're now instruction tuning or then it already like kind of like reflects on how good it is at following instructions. I would say it's very helpful metric. It's easy to calculate it throughout training, and you should monitor it. But it's not sufficient because you might have, a model checkpoint that gets lower a validation loss, but it might have overfitted to some subsets of the tokens in your validation set, and it might actually make it worse on the metric that really is really important. So I think the answer is like monitor it, but also check out other metrics.
Yeah, nice answer. I gave a way more shorter version of that. It went in great detail. I think another question that is important to cover here is it's talking about like should all be training based on prompt and completion. And if your task is if your final task is classification from text, and maybe should we be training with completion or not?
Can you say again, training with competition or completion?
Like autoregressive or causal ML, like generating next token prediction. If your final task is gonna be like sentiment analysis or classification.
I think that's a great question, and I would say, so these autoregressive language models that we're focusing on in this course, like their power comes in their like general purpose capabilities, right? So we evaluate these models, for example, on classification tasks, but we also evaluate them on the summarization. We evaluate them on code generation. So we try to comprehensively evaluate like what type of knowledge they have and how good they are at different tasks. But if your application is sentiment classification, then I don't think like in real life, like I would use GPT-4 for that. I would probably train a small BERT model and just focus it on the sentiment classification. But if it, on the other hand, like if this is part of like an agent and I don't know in advance what it's gonna need to do, and at some point it may like require to classify something, like it should have this capability. So I think if you are trying to develop a classification model, and you have a big data set and you can train on this data set, maybe take one of the encoder models. But if you want to build like this general purpose machine, then autoregressive models seem to be winning this battle.
And a final thought, a lot of people are asking like hands-on, showcasing how to run these benchmarks, because it can be very like overwhelming. And I will point people maybe to watch like a use lesson, and we went back and forth trying to run Humaneval and the Helm benchmark. And they require a lot of time and setup, and they are not that easy to run.
Yeah, that's a great point. And we encourage again to go back to the video from last week and check out like the code prepared by Ayush and yourself, Thomas, for evaluation. And if we have demand, I think we can do like a follow-up tutorial on running some of these evaluations hands-on, so we can do a lab session on that. Cool. I think we're at the point of the like at the time where we need to break. So thanks a lot for everyone for attending. We're looking forward. We'll try to answer all of the questions that come up either on Discord or in the comment section on YouTube. I think we would encourage everyone to join our Discord server. And yeah, thanks a lot, Thomas, for facilitating, for answering the questions throughout the session. And next week we're gonna have a break. We'll come back in 2 weeks on September 13th. We will have Jonathan Frankel, chief scientist at MosaicML, a person that knows a lot about training large language models. And Jonathan will talk about data sets for training large language models, which is an exciting topic. And I think I'm super excited to be joining the session in 2 weeks. So I hope to see all of you then. Thanks a lot, and have a great rest of your day.